Hi and welcome to this demo session about creating multi-axis additive toolpaths. My name is Richard Baxter. I'm Head of Sales and Marketing at MachineWorks, the software company that makes the Polygonica software libraries. As always, we're on LinkedIn. There's a company site for MachineWorks Limited and the showcase pages for Polygonica and MachineWorks. Please feel free to follow them, and you are very welcome to connect with me as well. So I'm going to give you first an overview of Polygonica's 3D curve operations. You'll notice in a previous video and blog we covered 2D hatch and infill for additive build processes. So this was planar infill as opposed to multi-axis infill with curved surfaces and this kind of thing. Also to say the example code that we're using for these demos that I'm about to show you, that's available on request if you want to have a look yourselves. And now some terminology. So a PT, we're talking here about PT curves. So that's a 3D polyline in 3D space. And a variant of that is a PT imprint curve, which is a curve lying on a mesh surface associated with that mesh. So a lot of the operations that work on curves work on the imprinted form of the curve, which means they maintain the imprint as the curve is modified. So for example, if you're offsetting the curve, it offsets it across the surface. If you're smoothing the curve, it smooths it on the surface. And the other point to note is that curves can have multiple loops, so they can actually represent enclosed material, etc. Within these demos, we're going to be using these four functions, are pretty important functions. The first one, PF solid pair create intersect curve, it's really part of the Boolean. So this takes two meshes and creates the intersection between the two meshes as a 3D curve. So that's a fairly fundamental operation. And then the second important one is create offset curve. So that takes an imprinted curve and offsets it tangentially across the surface, keeping an equal distance between the offset curve and the original curve. So it's a kind of Minkowski sum offset. There's also PF curve simplify, which is like equivalent to the 3D simplify in Polygonica. It reduces the amount of data based on a specified tolerance. So the resulting curve is no further than that tolerance from the original. And PF curve concatenate merges curves together. It can do that very simply just by literally concatenating the arrays, or it can actually merge loops and vertices to reduce the amount of data if you need that. Other curve operations in Polygonica, PF curve smooths the curve across the surface. This is really useful in some additive operations like support generation. You can see that in the image on the bottom left. So the bottom left curve is the non-smoothed curve, and the bottom right curve has been smoothed. PF curve extends the curve tangentially. PF curve close, self-intersection fixing, curve reversing. They're equivalent to the 3D healing functions for mesh healing, but operating on curves. And finally, there's a property of a curve loop, which gives you the area inside that loop as it's imprinted on the surface. There's a bunch of access functions. You can walk the topology of curves, so you can start with the loops and walk the loops, and then for each loop you can get the edges, walk the edges, and for each edge you can get the vertices, etc. So the code on the right gives you an example of that. And you can also use curves to create surface patches. These are polygonal surface patches, not NURBS. So given a set of curves, you can create a smoothly interpolated surface using linear or cubic interpolation. So now I'm just going to quickly run through the three examples I'm going to show you. The first we're calling it non-planar slicing to distinguish it from what's typically used in additive, which is planar slicing, where you're creating slices that lie in a plane, and then you do hatch and infill that lies in a plane. With non-planar slicing, the idea is that you take a surface that may or may not be a plane, and you move that through the part, creating the intersect curve with PF solid pair, create intersect curve. That gives you the intersection, and then you can use PF curve offset to create an offset toolpath inside that intersect curve, but moving across the intersect surface. So that's roughly what the image on the right is trying to show. You have the part in grey that we're trying to print. You've got the intersection surface in brown. You can see the intersection curve in blue, and then in red are the offset curves that lie on that surface. Extending that example to repairing worn parts. So in this case, we've got a sort of cuboid, but it's got a freeform surface on top, and we've had a chunk's been taken out of it. So you can use the Polygonica Boolean engine to take a scan of your worn part, and Polygonica, as the bottom bullet point says, Polygonica has a lot of great functionality for working with laser scans, including, very importantly, registration and alignment. So you can take your laser scan, tidy it up, align your parts, and then use the Polygonica Boolean to create a volume of material that needs to be added in order to repair that worn part. In this case, we then created a surface for the offset, a surface for the intersection by taking the top surface of the worn part and extending it using the Polygonica API PF Solid Extend, so it moves outside the region of the body of the solid body, and then we move it through the solid body and create intersect curves as before. So it's a fairly similar operation to the previous one, but in this case we're doing it just on a simple example of a worn part. And the final example uses Polygonica's 3D offsetting, which is very well known for being really fast, to create successive offset surfaces from the initial substrate. So in this case we're offsetting the golden propeller tip and intersecting it with the model of the blade in order to create a kind of smooth but curved surface on which to add material. So it's a similar process, it's just the way that we're generating the surface for each intersection is slightly different. So one thing to note, quite important, is that the path creation demo is done inside of Polygonica, or is done by Polygonica. But the actual simulation I'm going to show you is done by our MachineWorks product. So that's a dedicated software library for CNC subtractive simulation and machine tool simulation, and also additive simulation. So it's not part of the Polygonica product. So big letters there, MachineWorks is a separate product, not part of Polygonica. In fact, it even has a separate website, machineworks.com, which is this. Please feel free to go and take a look. And also the Polygonica website, so you can contact us through both websites and you'll get to the same people. We'll be happy to advise you on both libraries. Okay, so on to the demos. So now we're in Visual Studio and I've got these three little examples I'm going to run. So surface infill is the first one, so let me run that. So first thing to notice, this is a console application with a bit of built-in camera manipulation via the mouse, etc. So you get a lot of these on the Polygonica distribution, and they just show you how to use the API in certain circumstances, and some of them are reasonably involved now. I think there must be more than 50, I think. But this is an internal one. We don't give this out as part of the distribution, but if you're interested in this area, you're welcome to contact us and we'll send you the example. So here we've got the part we're going to print in transparent grey, and then this wavy surface is the surface we're going to print it on. It's a kind of arbitrary example. So first of all, we'll move the surface up through the part and create intersection curves using PF Solid Pair Create Intersection Curve at each level. So we've got the intersection curves there. Then when I click the mouse again, it's going to just, by way of example, pick one of the levels and then do an offset on that level. So let me do that, and there you can see. So the red is the external curve offset inwards using PF curve offset, and we've used a fairly wide step over there just so we don't create too much data for this demo. But you can see the blue is the intersection curve and the red is the offset curve. And if I double click again, then basically we can create that at every level. We have to redo the offsets at each level because of course the internals are different, even if the external curves might look the same, but of course they're not actually quite the same. But basically there we've got a set of points that can be turned into a toolpath. So let's see what that looks like in MachineWorks. So I'm switching to MW demo, which is the MachineWorks demonstrator. If you didn't listen to the first part of the video, MachineWorks is not part of Polygonica, it's a separate product. And this demo it's just an MFC demo, it's not available to buy or anything like that. I hope you wouldn't want to buy this. I wrote the original version of this in 1995 and was very surprised when I rejoined MachineWorks some years ago to find that it's still in use, but it serves a purpose. So first of all, I'm going to open my file. So LWN is just a kind of abstract G-code format that MachineWorks uses. So it's basically just tool motions or laser motions, if you like, in terms of X, Y, Z to move the tool tip, and IJK to position the tool axis. So let me load that in. You can't see anything because we haven't defined a base stock, but I'm just going to start that running. And you can see it's filling in using a fairly thick bead. So this isn't exactly the same one I did in the demo. We created this one earlier with slightly different parameters, but it's basically the same thing. Oops, sorry. Moving this while it's running is a little bit tricky. But there you go. You can see it's filling that in nicely. Let me just stop it, and that was running in single-threaded mode and updating the graphics every cut. This time I'll run it in multi-threaded mode and update the graphics every 100 cuts, which means that if you're updating the graphics every 100 cuts, it can do a bit of, it can make use of more cores, basically. So I'm running this on a 5-year-old Dell laptop now. It's a Core i7, but it's really, you certainly can't call it a workstation. And it's chugging along fairly nicely there. If you look down here, these are the tool motions it's going through, and it's got 41,000 it's got to get through. So it's got quite a bit of work to do to create this mesh. So I'm just going to stop that, and to save us time, I'm going to update it every 1,000. And I think in total that'll probably take about 40-50 seconds. So let me switch back to Visual Studio and show you the second demo. So this is the additive infill repair demo. So the idea here is we have an original part, which is a cuboid with a wavy surface. And then there's a worn bit. So this is the worn part, this big chunk has been worn away, and we want to add material to repair it. So first of all, Polygonica's Boolean is really good at giving you regions in which you can machine or regions in which you can add material. So in this case, you would take, like, for example, the laser scan of the worn part and subtract that from the original part, and that would give you a bounding volume of the area you need, of the volume you need to actually add material in, which is this golden part here. Because we can, we're just going to use Polygonica's standard slicing just to show a planar infill, which, there you go. So if you wanted to do that using a 3-axis toolpath or tool or whatever, then, which is obviously fairly standard in what you call it, normal 3D printing, then there you go. That's all very available for you. And to do the non-planar one, then we have to create some kind of surface on which to actually, put the material. So in this case, we're going to use the bottom surface, and we're going to take the bottom surface and then extend it using PF Solid Extend, which is what's happened. Apologies for the Z fighting there, but I think there's two surfaces right on top of each other. So we've extended it. You can see that with one of the Polygonica operations, and then we're going to move that up through the volume, and as we did before, create the intersection curve. So we're only doing it for the one. So there we've got the intersection curve, and now we can offset inwards to get a tool path or a path to add material. And so if I do it for all of them, then it's a bit hard to tell what it's doing in this one. But we'll run it in MachineWorks, and in fact I'm going to run several paths in MachineWorks just to show you what they look like. Okay, so this one's finished. and you can see there it's created a nice solid representation, and this is a solid representation. It's polygonal. That's how MachineWorks works. You can, I mean, I'm rendering it in flat shaded, so you can see what's actually been created here. Yeah, you can do Boolean operations with that. You can compute boundaries. You can do all slice it. You can do all kinds of things. Right. Yeah. Back onto additive repair. So let's do that one. So first of all, I'll run the planar repair toolpath. So there it is, and I'll just run it with. It's not that long, so I'll just update every cut, and you can see there's MachineWorks whizzing through, and it's creating again a nice solid simulation of the material that's being added on top of this surface. For what it's worth, I'll just speed it up a little bit when we get to the end. Okay, that's done. And then I can just display the original design part, so that's what we should have done. And of course, there's some solid material sticking out here, so we'd have to deal with that. And I'm actually going to export one of these into Polygonica and show you what it looks like in Polygonica, and then do some booleans on it and stuff like that in a moment. All of those things can also be done in MachineWorks. I've just not hooked it up in this demo. Okay. And next I'm going to show you the non-planar repair from the bottom, and I'll just do it with 100 again. So this is now doing 5-axis motions. Actually, maybe I will show it. Oh, and I've lost it, sorry. Bear with. Let me stop it running, and I will just stick it down to update every cut, just so you can see what it looks like. There we go. So that's it, doing its 5-axis motions there, which quite nice and nice to sit and watch. Calming motions. Oh yeah. Anyway, let me just set it back to 100 so I can get to the end of it. Yeah, you can see these things. This one's much smaller. It's only 4,000 operations as opposed to what the other one was, 50,000 operations. So there it's finished, and you can see there's some stuff we've got to sort out on the top as well. So let me save that to an STL file. And I think that's saved. Yep. I'm just going to check that. Yep, that's been saved. So I'll just quickly show you. 1707, 205, 17. Oh, sorry, yeah, 17 of the 5th, 205. Yep, there. The reason I'm doing that is that the MFC saving dialog seems to sometimes not add the .stl on the end, and then yeah, it's sometimes quite hard to find the file. Okie doke. And then I'll finally show you the top-down version of this, which is a bit prettier, but has a few problems, I guess, if you actually wanted to print real material. So let's run that. So again, this is the top surface moved down through the part as opposed to the bottom surface moved up, which is why it looks different. And of course, then you've got these gaps at the bottom, which you aren't really ideal, which is why the top up way of doing it would be better. But again, just showing that you know, we've got these different options. There we go. Okay, going to take a pause and switch to Polygonica. So now we've switched to Polygonica demo, which if you're a regular viewer of these videos, you'll be familiar with. So this again is a demonstration program. It's not available for sale. It's our demonstrator for the Polygonica libraries, not the MachineWorks libraries. Again, they're two separate products. So I'm going to open up that stock that I just saved. Let me add the details on there. So, oh, there we go, 17th of the 5th, 205, and it's 208 now. I just paused the video to give myself a break. And there's the in-process stock, so let me load that in. While it's loading, Polygonica also checks for mesh errors, so open edges, self-intersections, non-manifold edges. And if you look at these traffic lights at the bottom, you can see that it's all green. So MachineWorks here has created a good quality mesh. It's free from mesh errors. The other thing to note here is the number of faces, number of triangles in this. It's 721,000 triangles, so we're going to simplify that later on, just to show you that that works. But first of all, I'm going to do a Boolean operation. So let's open up the target. So if I just hide the stock, then this is the target. So this was the volume that we were trying to fill. And then if I show all again, and then I'm going to do a Boolean subtraction of the volume we're trying to fill from the volume we have filled, and that will give us this nice sliver geometry, which we can use, for example, to compute boundaries in order to constrain further, say for example, subtractive machining operations to tidy up the surface, etc. Okay, so that's a quick demonstration of the Boolean. Let me just hide that, and I'll also show you this simplification decimation that's in Polygonica. Typically, MachineWorks models actually do tend to decimate quite well. You will get, particularly subtractive ones, you'll get some quite nice results if you do that. So here I'm going to use a tolerance of 0.1. So that means that the resulting model will be no further than 0.1 units from the original. And then if we look here at the bounds, they are 100 by 60 by 40. So I don't, whatever those units are, we're doing 40 and we're doing 0.1, which is fairly loose, but it will give us a reasonable amount of decimation. So let me set that going. So the other thing to mention is this is going to introduce mesh errors, and that's because simplification, unless you set the option, like this option here, avoid self-intersects, unless you set the option, simplification is just doing what you tell it to. It's just removing or merging polygons. It doesn't do it. It doesn't try to keep the mesh integrity. So it's built for doing it quickly. But Polygonica has, and also the reason why we've got these mesh errors is, if you think about it, we've got adjacent beads, and as they're being simplified, then they're being shifted slightly, and of course they then overlap, causing self-intersections. So all perfectly reasonable. And Polygonica has extremely good automatic mesh healing, as many of you will know, and so it's no problem to sort this out afterwards. It's what I tend to do, or you can actually set the options when you do the simplification. So that's finished, and it's dropped down to 98,000, and I think it was over 700,000 when we started. So that's a pretty substantial reduction in number of polygons. And if we actually zoom in and have a look, you can see MachineWorks. So what MachineWorks creates is all controllable using tolerances. You can change the tolerance for every cut if you want to, or every tool motion. Obviously, most people don't. And similarly, you can loosen it for a fast preview or tighten it to get really, really accurate results. For example, if you're doing cutting force analysis or whatever. But here we've sort of set a kind of medium tolerance, and you can see what MachineWorks has actually created in polygons. Normally, I guess this is kind of hidden using smooth shading and everything, but and then you can see what we've simplified it to using Polygonica. So you can get a pretty good idea of the quality of both engines here, and they both use the same Boolean operations. So it's not surprising that it's fairly easy to transfer data between them, etc. Okay, so that's exporting MachineWorks into Polygonica, and I'm now going to move on to the last demonstration. So back in Visual Studio, and the one we want here is offset surface slice. So we're going to do some turbine blades. So let's run that. So we're just going to do one slice, or one sort of turbine blade on this bit of turbine, but we could do lots of them. It's all parametric. So we just created this using Polygonica itself. Okay, so first of all, the idea here is we're going to use offsetting to create the intersection surface. So here's the outside of the engine, and then we double click, and it's doing successive offsets and creating the intersection curves from them. I'm not sure this is how you would do it in real life. It's more a sort of proof of concept. Apologies for the graphics issues there. But that's created a nice set of curves. I mean, you could just use a radial one rather than actually offsetting this surface, but I think there are possibly cases where offsetting this surface would be useful. And then finally, we'll do the offset to actually create the curves. There's hardly any on here, but you'll notice that we do actually, in order to get the external surface, we do have to make sure that it's offset inwards, etc. Okie doke. So that's that one. And just look at that in MachineWorks. So what have we got? Propeller, single blade propeller. So there we go, and let's just set this to 1 because it doesn't take very long. And there we go, so it's nicely adding that, building up that material there. Yeah, so it's in this case it's only like 3,900 cuts as opposed to, or 3,900 additive motions as opposed to 40,000 was what we had before. And there's the result. And just to show you, there's the actual model we were trying to create, and you can see it's pretty close. And again, we've only done this with a fairly loose kind of set of tolerances, etc. Okay, so thanks very much for listening. I realise this has been a bit of a long one, but if you've got any questions about this, feel free to find me on LinkedIn and connect and ask me that way, or you can fill in the forms on our website and get in touch that way. So thanks for your time, and hope you have a good day.